metal iodine is often used to demonstrate sublimation, which is when something goes directly from the solid to the gas phase without a liquid intermediate. There are a few other common examples out there like dry ice or mothballs, but iodine tends to work better for demonstrations because it's so strongly colored. At room temperature, its sublimation rate is really slow, so we can't see the vapors coming off of it. However, if we put it in an enclosed space, the vapors can build up and get more concentrated, and we can see a faint purple color. This isn't very impressive though, so for the demonstration, the iodine's usually heated. As the iodine warms up, more molecules are able to make the transition from the solid to the gas phase, and a lot more vapor is given off. Then, I place a round-bottom flask filled with cold water on top of the beaker. The iodine vapors will deposit on this colder surface and reform the iodine crystals. Okay, so at this point, you're probably thinking, great, that's a pretty straightforward demonstration. What exactly is the myth that this video is titled after? Well, a lot of people, scientists included, think that because iodine sublimes, that it doesn't or can't melt, which is totally wrong. What I find interesting is that despite it being incorrect, it's still often taught in schools and sometimes written in textbooks. It's definitely up there as one of the most widespread misconceptions in chemistry. For example, I did a quick Google search and I easily found a few textbooks which propagate this myth. One of the saddest parts is that this book is literally just called iodine, but it still gets it wrong. Just as a comparison, here are some other textbooks which correctly state the complete opposite thing. What's kind of funny is that this one is also just called iodine, but it actually gets it right. Anyway, at this point, I'm kind of just telling you to not believe some textbooks and to believe others without any real evidence. However, I can actually prove it to you really easily. I'm just going to do the exact same demo that I did earlier, except this time I'll crank the heat up a lot higher. When I do this, you can easily see that the iodine starts melting. As I continue heating, everything eventually liquefies, and from that point on, it's technically evaporation and not sublimation. So if you actually want to be demonstrating sublimation and not just deceiving the students, it's really important to keep the temperature below the melting point. The boiling point of iodine is about 184 C, but the hot plate is a lot hotter than that. So the iodine starts to boil off, and the bottom of the beaker clears up a little. About a centimeter above the hot plate, the temperature of the glass is below the boiling point, but still higher than the melting point. Because of this, the vapor condenses back into liquid iodine and doesn't immediately solidify. Then it drips back down and gets revaporized. Okay, so for me, this is pretty good evidence that it melts and that a liquid phase does in fact exist, but to really just drive it home, I'm gonna do one last thing. I add a whole bunch more iodine to a beaker, crank on the heat, and quickly melt it. Then, while it's a liquid, I pour it into another beaker. If this doesn't prove that iodine melts, then I really don't know what will. Okay, so considering this myth is clearly wrong, you really have to wonder, where did it come from, and why is it so common that it even makes it into textbooks? Well, to explain this, we need to get into a little bit more detail as to what sublimation is.
Paris, Rome, New York. TUI city break sorted.
In all forms of matter, molecules are constantly vibrating, and the speed that they do this at is related to their kinetic energy. In solids, the molecules are constrained by a lot more forces, but they do still vibrate. However, a given solid doesn't just have one uniform kinetic energy, it's actually a mix of molecules, all with different levels. In sublimation, some of the high-energy ones are vibrating fast enough that they can overcome the forces keeping them as a solid, and they escape as a gas. For them to do this, though, they must be both near the surface and moving in just the right direction at the right time. This process generally occurs in all solids, but the rate is quite variable. It depends mostly on the strength of the forces that are keeping the solid together. For example, iodine's held together by relatively weak ones, so they're pretty easy to overcome. Whereas in something like gold, the forces that are keeping it together are much stronger, so the energy threshold is a lot higher. This in turn means it's less likely for molecules to be above it. In any case though, regardless of the substance, if we want to increase its rate of sublimation, we just need to get more molecules above the threshold, which is easily done by increasing the temperature. So this is exactly what we saw with iodine. I raised the temperature, the number of molecules above the threshold increased, so the sublimation rate also went up. Now, to take the explanation a little bit further, I need to talk about something called a phase diagram. Basically, it lets us easily work out the phase a substance should be in, given the temperature and pressure. A diagram like this exists for pretty much all substances, but for this explanation, I'm just going to use water. So the first step to using it is to choose a temperature and pressure. So for example, at a normal atmospheric pressure of 1 atmosphere and a temperature of -20 C or -4 Fahrenheit, water is solid, which makes sense. As I mentioned before though, all solids sublime, and this includes ice, even at -20 C. If the pressure stays the same and I just increase the temperature, the rate of sublimation will also increase right until we reach the line separating the solid and liquid phase, which is at 0 C. At this point, the ice melts because the molecules have enough energy to overcome the forces keeping them together as a solid. From here on, it's a liquid, but if I keep heating it, its rate of vaporization will continue to increase. Technically though, it's now called evaporation just because it's in a liquid, even though it's pretty much the same process as sublimation. Eventually, we get to the boiling point, where the pressure of the vapor coming off of the water is equal to the atmospheric pressure. At this threshold, most of the molecules have enough energy that they're ready to make the jump to the vapor phase. Okay, so that was just for water, but now let's take a look at the diagram for iodine, which actually looks pretty similar. I'm just going to be starting at room temperature and normal atmospheric pressure, which lands us squarely in the solid zone. When the temperature is increased, the sublimation rate also increases until we reach the melting point at around 114 C. Then, if we keep heating and evaporating it, we'll eventually reach the boiling point, which is exactly what we saw earlier. Okay, so from what we've seen so far, it really doesn't make sense to say that if something sublimes, then it can't melt. However, that's because in both the cases we've looked at, the atmospheric pressure is above the triple point. So what happens if the atmospheric pressure is below the triple point, like we have with dry ice? Let's say we start at around -100 C. As the temperature rises, as usual, the sublimation rate also increases. When it gets to around -78 C, the vapor pressure is already equal to the atmospheric pressure, and it wants to turn into a gas. This is exactly like what we saw with the boiling point of water and iodine, except this time, the boiling point is below the melting point. This occurs because the melting point is dependent almost entirely on the substance alone, whereas the boiling point depends on the substance as well as the outside pressure. It just so happens that the atmospheric pressure we live in places it along this line. If I wanted the dry ice to melt first and then boil, I would have to increase the pressure to somewhere above the triple point. In any case though, when it gets to this boundary between the two phases, the process that it undergoes is similar to what boiling is for liquids, but to differentiate it, we call it sublimation. But wait a second. Earlier on, I told you guys that sublimation was a process that happens in all solids, and it's similar to evaporation. But apparently now I'm telling you it's similar to boiling. How does that make any sense? Well, basically it doesn't, and that's exactly the problem. With liquids, we have two different words, evaporation and boiling, which describe two distinct processes. But with sublimation, for some reason, we only have one. So because of this, it's kind of true to say that if something sublimes, it can't melt, and it all depends on which process we're actually referring to. Some resources try to get around this problem by saying that below the melting point, it's still called evaporation, claiming that sublimation should only be used to describe the proper phase change when something's below the triple point. However, I think that even if everyone did use these definitions, it would mean that we have one term, evaporation, applying to both liquid and solid phases, which might also cause some issues. I'm going to use Wikipedia as a quick example of how wishy-washy the definition is. On the page for sublimation, it starts by defining it as only occurring below the triple point. Okay, so that's off to a good start, but then it goes on to say that it's also just the generic transition from solid to gas. And for the rest of the article, it just uses both definitions interchangeably. I think to solve all this confusion, we just need to make a new term that exclusively describes the evaporation of solids. The term sublimation would then only describe the proper phase change that occurs below the triple point. Just for fun, I took 2 seconds to make up a word based on my channel, and I called it nihilation. This way, iodine no longer sublimes, it would nihilate instead. Dry ice would nihilate at temperatures below -78°C, and then it would sublime. In my opinion, this could prevent a lot of confusion, and it would also wipe out the iodine myth. Let me know what you guys think of my made-up term, and let me know if you think something else would be better. In theory, if we all started to use a new term, whether it's nihilation or something else, we could probably eventually change things. A big thanks goes out to Squarespace for sponsoring this video. They're offering a free trial for all my viewers, which you can get by going to the special link, squarespace.com/nilered. Anyway, with that being said, what is Squarespace? Well, it's a really easy to use and intuitive website creation tool. They offer a lot of templates and different options to build your website just how you like it. Personally, I use Squarespace to run my own website, and from the moment that I decided to have a website and a shop for my channel, it only took me about a day to set everything up. What I like the most is that it's really simple for me to track and manage my store inventory. If I ever need to change or add anything, it only takes a few clicks. Updating general information, text, and layout is pretty easy as well. Everything's done intuitively, and again, there's no coding required, there's no plugins, updates, or patches or anything that you have to worry about. Anyway, in general, I honestly really do recommend Squarespace. If you're interested in making your own website and supporting me at the same time, you can get your free trial by going to squarespace.com/nilered.